Good morning, everyone. Today we'll see what is fuzzy logic. As the name indicates, fuzzy logic is used in AI for modeling uncertainty or some kind of vagueness into input. The fuzzy logic generally converts the crisp value, like for example, if you say 6.5 is a tall, to a linguistic variable like if when you say high, low, cold, hot, these are the linguistic value. It has situation specific meaning. For example, the cold and hot will have a different meaning in a different case. If somebody is standing at Antarctica and saying that it is very hot, probably he means to say that this temperature is between somewhere 1 or 2 degree. If somebody is standing here in Sherpur in the month of April or May and saying that it's too hot, that means the temperature is above 40 degree. So this is relative. The hot and cold are known as a linguistic variable. Now, converting this linguistic variable into something which can be programmed, which can be modeled. This is what the fuzzy logic. The fuzzy logic has capability to model this kind of vagueness or uncertainty. If there are the uncertain measured values due to the situation specificity or due to any factor, if the input of the variable is vague, in such cases we use fuzzy logic to model the system. The fuzzy logic is invented by Lobzadeh in 1965. It is based on the system of non-digital set theory and rules. The theory deals with the continuous and fuzzy without crease boundaries. Means you can create a fuzzy system for a continuous variable or a discrete variable. It is developed to deal with vague system, as I already told you, and it uses the linguistic variable. The linguistic variable, the values or the parameters which we use in our day-to-day life, as I told you, hot, cold, tall, short, good, bad. So these are the linguistic variable. The good, bad, or short, tall, it has a different meaning to the different in a different context. So the fuzzy logic is used to model such linguistic variables because there are certain type of vagueness associated with it. When somebody is saying tall, if you don't know the situation, you cannot exactly tell the meaning of the tall in a given situation. So what does the tall means? Whether it means if he is talking about the trees and a tall tree, whether it is 10-meter height, or if he is talking about some person, it is 1.2 meter. So like this, the model such kind of vagueness, the indefiniteness, we use fuzzy system. Before we jump on fuzzy, we need to have some revision of the relevant content. That relevant contents are the set theory and a logic theory, a logic system which we already studied. So I will revise the theory of a set which we have not studied so far. The set is an unordered collection of different elements. I think we all know this definition, but we'll be using this is the fuzzy set. So this definition is for the crisp set. Crisp set means where we have a discrete elements into a set defined by some relation, like say set of all alphabets or set of all odd numbers as indicated here. So like this set of all vowels in English alphabets. So it would be A, E, I, O, U. So these are all discrete variable A, E, I, O, U, and they are unordered. So there is not necessary to write this in a particular order. So set of odd numbers here. So less than 10, they indicate by B. Again we have a discrete variable. This is a set. Set is described as A is equal to all the element X such that the P of X holds true. The P of X is the condition which the variable X need to satisfy to be member of this set. So the condition may be, for example, here in this case, the odd number set we have checked if it is between 1 to 10 and if it is divisible by 2 and the remainder is not 0. So that is how we identify the odd numbers. Some of you may use some different logic. So this P of X would be this condition. Number should be between 1 to 10. If we divide it by 2, the remainder should not be 0. So that is the logic we use to decide whether the particular element X can be a member of this set or not. The cardinality of the set is denoted by this symbol. You can denote it like this. The cardinality of this set 1, 2, 4, 1, 4, 3, 5 is 4, and this set is infinite as is a set of natural numbers, so there are infinite natural numbers. Let's move further. The operation which we can carry out on the set are, we can overlap the set, we can disjoin the set, we can join them, that is union, we can find do the intersection, we can find the difference between two sets, complement of the set, and we do a Cartesian or a cross product. These are the different properties of the set. Commutative property like A union B is equal to B union A, or A intersection B is equal to B intersection A. So that is called commutative property. Associative property, distributive, here the representation, and the finally De Morgan's law. So these are the different set properties we need to recall. Now let us understand how the crisp set, or what you call it as a Boolean set and fuzzy set, differs in operation. For example, here I am representing a crisp set, or the Boolean logic is RAM honest. So it can have the two possible state, a Boolean state. RAM is honest, yes or no, true or false. Let us indicate yes by 1 or true by 1 and false and no by 0. So these are the two possible outcomes of a Boolean logic. If I represent the same set with a fuzzy logic, it will have a different representation as indicated here. So here you can see the is RAM honest has multiple outcomes, intermediate stage between 0 and 1. So with this Boolean logic, we will not able to identify how honest the RAM, how honest is the RAM. So here in this case, we can measure the honesty level. So that honesty level is an essential criteria to be member of this fuzzy set. So here the essential criteria is either he is honest or he is not honest. But the intermediate stages, suppose for being honest, if you have a score 0.9, probably the RAM is still considered as not honest. So here in this case, in fuzzy set, so extremely honest will have the value 1, very honest will have, let's say, 0.85 and so on. So this membership value is referred as degree of the membership. So what is the degree of a particular element of being a member? For example, I want to classify you all into a MBA Tech CS third year. So what is the everybody, if you do it with the Boolean logic, everybody of you are a member of this set, this class. But if I want to measure the degree of membership in terms of the fees you have paid, the classes you have attended, percentage you have scored, so everybody will have a different degree of being a member in this class. Some will be 100% members, some will be 90%, some will be 60%, and so on. So I can measure to what extent you belong to a particular class. Let's say all students, 60 students, 62 students of our class, I think 69 students of our class, what is their degree of membership for this MBA Tech CS third year class. So that degree cannot be measured with the Boolean logic or your crisp set, but we can have that membership degree with a fuzzy logic. So fuzzy set is generally denoted by its degree and the element. Here U is the element and the letter M here indicates the membership degree. There are various other representation. We can represent this in the function form, or we can simply represent like this: fuzzy set A, generally it is referred as A bar. So fuzzy set here you can as seen below, membership function of fuzzy set A bar is equal to this y is the element and this is u of A bar of y is its membership degree. The condition is y belongs to U universal set. So this is a representation of a fuzzy set. So on this is on this axis we plot the membership value, that is 0 to U, 0 to 1, that is U, the membership degree of the fuzzy set, and 0 to Y, that is the variable or the element which would. So here A bar would be represented like this, the set of all members belonging into this category. So classical set membership would be like this. Means either it is the element of the set or it's not an element of set. But for A, so the elements which are at a different place probably, so suppose this represents let's say 0.5 and this represents 0.9. So all the elements between this 0.5 to 0.9 are the elements of fuzzy set A with its degree of membership. So this element would be, let's say, 0.5 comma 0.5 means this membership value is 0.5. This is a 50% member of this set. 0.9 means the element here would be 90% member of this set. That is how we represent the fuzzy elements. The fuzzy operations, as we have carried out the various operation on the crisp set, similarly we carry out the operation on a fuzzy set as well. Union of the fuzzy set, it is represented fuzzy OR, so it should be member of this or member of this. So if you plot this, let's say this is a set A represented like this, and set B, if you do a union you will get something. The common elements are eliminated here. So the A union B of a fuzzy set is represented by we have the membership degree of A minus membership degree of B. So that is for all Y which belongs to set U. This is union. Similarly, intersection. So A union B is represented A and B. So it is ANDing operation. So intersection is represents the common element. In previous slide you have seen this we have eliminated. So this minus remaining element is union. Like A membership, we compare the membership degree, not the elements, that you need to keep in mind. So we are comparing the membership degrees. Complement, there is 1 minus membership degree of the particular element. So complement would be represented like this. Then this is the features of the various features of the fuzzy membership function. The values which are exactly having value the membership degree 1 is referred as core. The boundary conditions are the values which are less than 1 and greater than 0. So here the membership, this portion, this particular portion and this particular portion are the boundaries, because here the membership degree, if you look at this, this is one line, membership degree 1, this is membership degree 0. So naturally the point below this line will have a degree of a membership less than 1. Similarly, here the points here will have greater than 0, just above the line. So membership degree between these less than 1 and greater than 0, all the points here lying on this line would be called boundary. The support would be the values, all the membership degrees which are non-zero, which are greater than 0, that is support of the fuzzy system. So these are the characteristic of a membership function. First is core, which is having the membership degree 1, boundary of a membership function where the value lies between less than 1 and greater than 0, and the support is all non-zero values. So these are the three characteristics we need: boundary, core and support. We'll understand it by one simple example. Let us see, try to design the automotive speed controller. Now I want to drive a car with automatic driver, which is implemented using fuzzy logic. So what are the inputs possible for this automatic fuzzy logic controller? There will be speed. Let's say we have 5 gears, 5 levels of the speed, 3 levels in acceleration. We can use acceleration in 3 steps. Distance to the destination, again we have 3 levels. Output will be a power. If we change the combination, power, that is fuel going to the engine, is getting changed. So set up rules to determine output based on input. Let us design the fuzzy system for this scenario. Fuzzy logic system would look like something. The speed, we have 5. Let us represent this in a linguistic variable. The first speed between, suppose label this value 1 to 50 is too slow. Here this too slow. Then there is some common portion between too slow and slow, and the values between this would be, let's say, slow. Then optimum, fast and too fast. So we have the boundary conditions which are overlapping. So this is vagueness of the system. This part, this overlapping condition between too slow to slow, slow to optimum, optimum to fast, and fast to too fast, these portions will be overlapping condition. This portion we label as vague portion, whether it is to be called too slow or slow. For this, the values lying between this, what it is to be called, that is the fuzziness of the system. Then acceleration, as we have seen, there are 3 conditions. The acceleration between this, let's say this is 1 to 50, that is called deaccelerating. So between this it is constant, let's say it is 40 to 60. Then accelerating when your stage is between, let's say 50 to 100, it is acceleration. Then similarly for distance, very close, that is the condition. Then close, again it has a lot of overlapping, and at a distance, it has huge distance between them. So this is how it is represented in fuzzy linguistic variable. Now let me tell you one concept, that is fuzzification and defuzzification. Converting crisp variable into a fuzzy variable is called fuzzification, and converting a fuzzy variable into crisp is called defuzzification. For example, if I say it is 10, so identifying whether 10 is high or low, converting 10 or associating 10 with its degree of membership by considering its degree of membership 2, whether it is high or low, is fuzzification. But if I say high, estimating its value is defuzzification. If I said it is very high, so finding out the membership value at the given scenario and telling me that it is 9. 9 means high. So that is defuzzification. So conversion of CRIS value, quantified value, to a linguistic variable is fuzzification. And converting this linguistic value to a CRIS value is defuzzification. So let us go ahead with this. How we can design a system, a fuzzy logic control, if speed is too slow and acceleration is deaccelerating, then increase the power greatly. Now how to increase the power greatly? We have three possible 5 power situation. Then if this is again linguistic, power greatly, what does the greatly means here? How much accelerator I should press? That is fuzzification. If speed is slow and acceleration then increase the power slightly. If distance is close, then decrease the power slightly. So these are the fuzzy representation of the business rules. So output would be something like this. Degree of a membership is an output fuzzy set, now represents each fuzzy function which we have just discussed, like decrease power greatly, decrease power slightly, or and so on. So here 0.3 membership value represents increase slightly. 0.7 indicates leave constant, and 0.7 and above indicates that increase greatly. So similarly, these are the action possible with the logic, this logic. These are the rules. With this rule, these are the actions possible. These all are the action possible. Decrease power greatly, decrease power slightly, leave the power constant, increase power slightly, and increase power greatly. Okay. So now the fuel supply is represented on this x-axis, and the fuzzy membership is represented on this axis. That is, fuzzy membership will be between 0 to 1, and the power supply would be, let's say, scaled on to scale of 0 to 100. So you have different representation of each stage. Now you will make a rule. If you lie here, if you want to reach here, what is the rule? Apply rule number 1. Let's say increase power greatly. What it means? So you can find out the quantified value of increase power greatly. Mean, suppose here it is 90. So fuel supply should be running in 90% capability. If you look at this, if you are currently here, that means fuel supply is 90%. That is defuzzification. So increase power greatly at this point. This is my situation. I am currently here. Then in this situation, increase power greatly means fuel percent should be 90%. If I am here, it means a different thing. If I am here, it means a different thing. So fuel supply should here would be somewhere between 80 to 90. So like this, we are trying to model the fuzzy system. Now we'll look at how does the fuzzy membership function looks like. Fuzzy membership curve defines how each point in the input space is mapped to the membership value. What it means? It finds out, suppose you have all the elements on x-axis representing the member of the fuzzy set, and again the membership value onto y-axis. So you will get a fuzzy representation somewhat similar to this. What it represents? What is the behavior of fuzzy system? We have seen these are the boundaries, this is the core, and the whole is the support of the fuzzy. The boundaries are the membership values between 0 and less than 1. Core is membership value exactly 1, and support is all non-zero. So that this area would be a support. Then, as we have designed inference engine in export system, very similar to this, we have a fuzzy inference engine. The components are rule base. In the knowledge base, we have rule base where we define the rule based on the linguistic variable. If it is very high, then reduce. If the speed is high, reduce the power supply or fuel supply greatly. So this kind of rules we store here. Then this the outcomes of the current stage and the historical data will be stored here. That is your knowledge base. Then we have two units. One is fuzzification, as I told you, converting the crisp variable into a linguistic variable. 10 means high, like this, converting a crisp value into linguistic variable at the input in. Whatever we measure, suppose we have some sensor which are measuring the speed, it will measure the speed in a crisp variable like 10, 20, 100, 110 kilometer per hour. So that speed has to be converted into some linguistic variable, slow, fast, very fast, like this. So this process is done by this fuzzification unit. Whereas once it takes a decision and if it concludes that if speed is very high, then reduce the power supply to reduce the speed. So reduce the power supply, that is fuel supply, greatly. That means you should supply only 10% fuel to the engine using acceleration steps. So what is that reduce the power supply greatly means, like you need to quantify it, how much power supply you need to reduce for actuators. So actuator is your accelerator in this case. So how much what should be the position of acceleration so that it can supply. So you need to quantify it, convert that reduce greatly to some linguistic reduce by 90%. So we need to quantify. So this process is called as defuzzification. So these are the two units: defuzzification, where linguistic variable are converted to crisp variable, and fuzzification, where crisp variables are converted to linguistic variable. And based on this fuzzification and defuzzification, we implement various kind of decision making. So this is fuzzy inference engine, and we in this fuzzification and defuzzification we design a fuzzy logic controller. So along with whatever we have seen in a previous slide, we have sensor and the actuator. So input will be sense and it will pass to this fuzzification and the rule based system. Then it will be defuzzified, and defuzzified output will be passed to the actuators or the plants which can adjust to the situation. So this is a typical fuzzy logic controller. Now various fuzzy logic applications. Fuzzy logic can be used in various business conditions. For example, aerospace, the automatic altitude control of the spacecraft or a satellite control. In automotive, trainable fuzzy system for ideal speed control, scheduling various kind of activity, intelligent traffic management system, traffic control system. So wherever we have some kind of vagueness, I think in all such situation we can use a fuzzy system. So decision making support system for a businesses where some parameters are vague, like if I promote my product on this particular media, if I have this particular feature into my product, whether how much quantity I will able to sell. So there is a vagueness into input variables, this feature or some or other. If there is some vagueness we want to model, then we can use a fuzzy system. There are many other applications in defense as well: target recognition, various kind of decision support system in medical to establish a pattern where there are overlapping pattern for two similar disease to identify this pattern corresponds to the X disease or Y disease based on his membership degree. So this is the vagueness, the overlapping region. Suppose in defense they want to identify a target, but the target looks like the passenger ship or whether it is the enemy ship. So the similarity, based on the similarity, finding the its membership degree, it belongs to enemy ship or let's say passenger carrying vehicle. Various kind of pattern recognition where you have a vagueness, a fuzzy system can be used, like the similarity score is high with a traditional technique is we cannot detect to what extent it belongs. For example, if you the Boolean algebra or your existing logic, if I calculate your membership of this class, it will be either 1 or 0. But some, no, this is not the case. Some of you are based on the parameters, like for getting into the class, how many subjects you have to pass, how much fees you need to pay, the attendance. If I give the weightage to it, so membership degree of each member in this class will be different. So that is such kind of vagueness if you want to model when there is some overlapping to discriminate the elements when there are overlapping boundaries. In all such situation, a fuzzy system can be used. Thank you very much for watching this video. I hope it has prepared you for, it will prepare you for the exam.